So another abstraction that we're going to use, which you've used before, are the abstractions of volume, surface, and line charge distributions. So there's going to be a rho of R, which is a volume charge distribution. There's going to be a sigma of also position, which is going to be a surface one. And traditionally, we do a line charge distribution as lambda of R. Charge distribution. Okay, again, I presume you're familiar with this. So the electrical field produced by a volume charge distribution at a certain position R is just now 1 over 4 pi epsilon 0 by the principle of superposition, the integral over all non-vanishing places of this volume charge distribution of the volume elements. I'll write it d tau prime. So prime coordinates are kind of the source coordinates here. Rho at R prime. And then simply the R minus R prime divided by R minus R prime cubed. Okay, that's equation E, volume charge distribution in the notes. Okay, and this one has a light green box on it. Okay, so you're happy with this as well. You've used these notations before. So d tau is a differential volume element. D tau rho is the amount of charge contained in that differential volume element. And its contribution to the electrical field is d tau prime, so at the position prime, d tau prime rho at R prime with the usual 1 over R squared, but in the direction what? But by principle of superposition, just summed up over all available charges. Okay, so this is also, you've used these notations before? Yes, no? Question? D tau is the differential volume element in your chosen coordinate system. Okay, so I'm not writing what it is, but if you're using Cartesian, it's dx prime, dy prime, dz prime, where x prime, y z prime is the position of your source. Okay, so R here you could view as x, y, z. That's the position where you're measuring the field. But your field comes from a chunk of material that is charged over there. And the R prime position is over there. Right? So it's kind of a standard habit. If I use prime coordinates, usually it's referring to the source things. Okay, but you have to be able to see it from the context as well. So that's the volume, and we also have the surface and line equivalents that we can write quickly. So this is for right. This is for the volume. If we had the surface, then we would have just a very similar thing. We would have E at R being a point in three-dimensional space, but now with a field coming from a surface distribution. So think of, the plates containing charge. And now what I would have is an integral over a certain surface S, whose differential surface element dA prime, has a surface charge area that is a number of coulombs per square meter at this position R prime. And now again the same vector dependence, R minus R prime divided by R minus R prime cubed. Okay, so that's for a surface, and for a line it's just exactly the same thing. But now instead you've got an integral over a certain path P of an element dl, which parameterizes your curve, that has a linear charge density, that is a number of coulombs per meter, dependent on the position at which it is r prime. And again, the same dependence as here. Okay, so E volume charge distribution, E surface charge distribution, and then E line charge distribution. Okay, you'll find those in the notes. Okay, good moment for a little break, unless there are questions about this. So I am assuming that you have used those recognizable notations in the past. Okay.